So I want to go ahead and show you a demo of this new feature that we're landing in the containers bootc project. Here's the documentation page. This is currently an experimental feature, but I'm excited about it because it's a fundamental change to bootc. It's switching the way bootc works from managing one bootable OS container image to managing that base image, but that base image can now reference application containers that you define through a familiar systemd style podman systemd unit, and bootc will take care of managing the fetching those images and ensuring that they're present from the very start of boot and managing their garbage collection. They continue to be run through podman. Let's go ahead and take a look at this pull request I have to our examples repository. In this demo, what we are doing is let's go down to the container file. First of all, I'm actually updating the build to the latest bootc from git main because the latest on this feature is currently still in git main. This is a kind of continuous build. This pattern you'll see a lot in our examples. We're copying the config files from the /user directory that's stored in git to the target image. This gives us a way to just configure a bunch of things at once. In this case, just some systemd, podman systemd units. And then we have a little bit of code to add a symlink for those, and I'll get back to that in a minute. Let's take a look at the two containers. So a primary example use case when you might want to turn to logically bound images is where you have a container image that you always want to be present on boot. Like you think of it as logically part of the operating system. In a lot of operating systems, the web server and client operating systems, the web server and the OS may be versioned together and come together as a single unit. They have a single version number, but they may be delivered separately. In this example, we're running the Prometheus node exporter, which runs as a semi-privileged container. And here you can see I've just translated the upstream examples for how to invoke Prometheus into a podman systemd.container file. There's nothing too exciting about this. The only thing I would call out that's of interest here, there's two parts actually. One is that with logically bound images, we expect you to reference an immutable version tag. And the reason for that is because bootc doesn't handle floating tags today for these. We expect that when you rev the version of these, you change the version you're storing in your GitOps flow. The second important aspect of this is that you need to tell Podman to look at the bootc image storage. So there's a new user-lib bootc storage, which is a container image store that's owned by bootc. So that's Prometheus, which gathers metrics from the host and that can be scraped by Prometheus server. And then finally, we have a demo web server. I happen to use the stock caddy image that's published on Docker Hub just because it's maintained, it's multi-arch, and when you run it, it has a demo web page. Like I don't need to go and manage a custom container. So you can see the only thing that's interesting about this is we've injected the additional store into the ops. So yeah, that's basically what this container build does. We copy in those systemd unit definitions. And then this invocation is saying we basically create a symbolic link in the user-lib bootc bound images directory to those .container files. And that tells bootc to take care of fetching the image that's referenced here. Again, bootc doesn't run the containers. That's still the job of Podman, but it takes care of fetching and maintaining and garbage collecting the images. So I already built a container from this pull request, just in the interest of expediency. Here it is in a VM. For the interest, this was through podman bootc run, and that spawned a local VM. So let's go ahead and look at bootc status. So you can see here, yes, I'm running that image. Now, let's look at systemctl status node exporter. You'll see. Yes, of course, the container, the image is running. If we look at podman ps, we'll see our two images with the expected tags. All looks good. But let's go ahead and look at podman images. You'll notice here, they actually don't show up when I just type podman images. And the reason for that is because the bootc storage is not explicitly configured. So what we have to do now to get visibility here is pass that same option, additional image store equals userlib bootc storage. So now you can see when I told this podman invocation about that additional image store, notice the read-only flag is true, okay? And that's because indeed, everything under the /user, everything under the booted root file system appears read-only to most host management software. So, if I try to write it, the storage, yeah, it's all going to appear read-only. So now, when I type bootc upgrade, it's going to check for changes to the base bootable bootc image, as well as all logically bound images. So basically the flow is bootc will go, when there's a change, bootc will go fetch the new base image, and then it'll look for updated bound images and pull them. And those will be applied on boot. So let's go ahead and make a change. Now, here's an example of looking at the Quay page for the Prometheus node exporter. Now you notice I intentionally chose the v181 tag. So as you'll normally want to do, you want to, again, have like a renovate or dependabot style flow to update these dependencies. So let's go ahead and play the role of that. And when I look at the node exporter container, so let's go ahead and bump that tag, right? Where you saw the change that I made here, I just changed the 1 to the 2. So look at the git diff. Now I'm going to go ahead and, oops, I'm in the wrong directory. I need to, yep. Let's go ahead and build a new version of that image. And you notice, actually, I already had this cached because I had already built it in preparation for this. So now I'm going to go, but what I'm going to do is I'm going to update my copy on Quay. I'm going to push what I had locally, and now I have a new image. Now, when I type bootc upgrade, it's going to fetch the new image. And actually, the reason it's fetching all layers is because I had this initial build from an image that was built locally on my machine. So with Podman bootc, it will use the uncompressed storage, and we don't yet know how to when we do the transition from the uncompressed storage to a remote repository that's compressed, all layers will appear changed. But normally in the flow, once you've shipped production bootc, you'll always be using a compressed image and not one that you built locally. So we'll only see a small change. And I can demo that when I go back to revert the version. So now notice bootc, we fetched that new base image, and right there you saw us fetching the 182 tag. So now, of course, we didn't change the running system. If I look at Podman PS, the container is unchanged. It's still using the 181, and that's what we expect. Now, if we look at the images, we see the new image is there. So let's go ahead and reboot. And again, by default, bootc has a simple systemd timer that I could also wait for that to fire, but I'm just invoking the upgrade manually. And now when we go back into our machine, what we should see here is the updated, yes. If we look at Podman PS, we'll now see that we're running v182. But an important aspect of this, if I look at the images again, v181 is still there. And the reason for that is because bootc still has a rollback deployment. So bootc will only garbage collect those images when all bootloader entries for it are gone. So if I were to clean up that rollback deployment or make a subsequent upgrade, and in fact, we can kind of do that by doing another build and testing this out, we would see that the older image got garbage collected, the v181. So this is a powerful way for you to continue to use containers for things that logically feel part of the operating system. Again, now we continue to expect use of what I call floating container images that you manage out of band. perhaps this is a Kubernetes node and you have a lot of dynamic workloads. You wouldn't use bound images for those. You use bound images for the things you expect to update on the same cadence as the OS, at the same cadence you take reboots in general. And so this gives you a powerful new tool in the toolbox. Again, we're changing bootc from managing one image to multiple. And that gives you a lot of new power and flexibility. And that's it for the demo.